Hello, AP students. Hopefully you have power later this evening and you can watch this video and take your notes. Okay, so we're going to talk about chemical bonding. We're starting to get into the language of chemistry, writing the different names and formulas. So we are going to take time to now learn about chemistry, making chemical bonds. What type of bonds are there? How are they made? How do we differentiate them? All sorts of stuff. What are the characteristics of them? So, chemical bonding has to deal with our lovely ADHD electrons. Electrons cannot sit still. They are constantly moving. So, chemical bonding is a representation of what happens when an electron is either moving from one atom to another, causing an ion, or traveling in the space between two atoms and shared. It can be shared equally or it can be shared unequally. So there are different ways that an electron behaves to facilitate this thing called bonding. So let's get into discussing some of them. All right. Again, movement of electrons, going from one thing to another or moving around two things equally or unequally. So a lot of this bonding happens because atoms like to have a full outer shell. They like to get that S and P orbitals, hence 8 electrons, 2 for the S, 3 for the P. This is where, I keep talking. Valence is S and P. Valence electrons do the chemistry. When you look at periodic trends, things in a group, column, have the same number of valence electrons, so they behave the same way when they make a bond. Okay, so S and P electrons are involved in bonding. Under special circumstances, the transition metals, other elements that are very deep in the table, they can use empty d orbitals, empty f orbitals to make space for other electrons so they can make a different kind of geometric bond. Okay, so spatial. And we're going to get into spatial towards the end of this topic. So the first desire of the atom is to get that stable outer octet, all 8 electrons in the S and P. So one way to do this is to gain electrons, and that would be things that are nonmetals, and another one is to lose electrons, and that would be metals. You can also share electrons, which is a different kind of bond. There is something I have to get straight with you guys that, like I said, you're sometimes misled in bio, because bio talks about an entire system when they talk about creating energy in a cell. For instance, the Calvin cycle? I think it's Calvin cycle, where you do the ATP to ADP, and they're like, oh, when you break that bond and you lose that bond, you create energy. That's a fallacy. That is wrong. It is not the breaking of that phosphate connection that makes the energy. It is the whole process where you have bonds broken and bonds formed, rearranged and formed, that the net outcome is a creation or a loss of energy. All right? So you have to be very careful, and you have to get this into your head. When you break a bond, right, a breaking of a bond requires energy. You have to put the energy into the system. Think about holding one of those wonderful number 2 yellow pencils in your hand. Let's pretend that pencil is a bond between your left hand and your right hand. And you want to break that connection. So unless you put force into that and snap the pencil, you stay together. So to break a bond, you have to put force in, which we will measure as a form of energy. So you put energy into that attraction, and you disrupt the attraction by breaking it with enough energy. So you put energy into the system to break the bond. On the opposite end, once the bond is broken, often bonds in a system will rearrange. So we're not talking about one little molecule isolated in space. It breaks one of its bonds. No, we're talking about a system, lots of molecules, lots of things, reactants, products. One breaks a bond and moves over close to something else. The other thing breaks its bond and moves close to the first thing, and then they make new bonds. And when you make a bond, energy is released. Okay, so very different than what you've been pounded into your head by bio. Okay, bio's wrong. Some people say, well, not really, it's perception. But it's a net thing in bio. It's not an individual thing, and they say it as if it's individual. And it's a net action. And we're going to talk about net actions with relation to energy later on in the year. Around about February, we start to talk about looking at entire systems instead of bits and pieces. Right now, you're going to get bits and pieces. And around January, February, we start making connections between the bits and pieces. Right? That's why I say you cannot forget what you learn, because when January comes, it's like, whoosh, all of a sudden we put it all together. Okay, so when you make a bond, you release energy, and that's a huge thing. You release that energy and you create essentially energy. And that's really what happens in that Calvin cycle. You rearrange the bonds and the net outcome is a release of energy. So let's look at a system. And it's hard for you to see this. Oh, I'm gonna write it off to the side over here. If I have H2 and I add to it Cl2, I will make what's called HCl. Okay, so that's this part right here. And we're missing the L over here, so I'll change my pen. And I'll make it, this is the closest color. We'll put the little L in here. Whoops, sorry about that, guys. I don't have my little glove on, so every time my hand touches the screen, it's going to move the screen. And I don't want to waste the time putting the glove on, because I only have battery backup for my internet for so long. Okay, so when you look at that whole system, we have to break the diatomic bond in H2. We have to break the diatomic bond in Cl2. We're putting energy in. We rearrange and we make two new molecules of HCl. Okay, starts with an H. So that's an acid. Right? If we're going to name it, it's hydro because it's binary, chloric acid. When that makes that bond, it'll release energy. If this energy that's released is greater than the two of these added together, then we call it an overall net release. If the ones in the side to break the bonds is more than the one that's released, then we have to put energy into the system. So it's all system dependent. Okay, so keep that in mind. Try to start thinking about that now before we get to writing equations and looking at energy transfer. Break a bond takes energy. Makes a bond releases energy. Just keep saying that over to yourself so you get that down. Trust me, AP asks the question and Regents asks it in many forms, because Regents knows when you take living environment, you're told the opposite. So let's see if the kids relearn what it means to break a bond and make a bond. Kind of dirty on their part, but valid assessment. Okay, so now we have one situation where we transfer the electron. The electron moves from the metal to the non-metal. Right? So if you see a metal, you always ask what makes it. What makes the material? If you see a metal with something else, and then I'm going to use this dash attached to anything else, that has to be ionic. If you see a polyatomic ion, that has to be ionic. The electrons have to transfer. Okay, so just realize that. A metal with something else, polyatomic ion anywhere, because polyatomic ion means ionic. Look at the root. Okay? If I have a cation and an anion, then I have to have an ionic bond. One of the ways we look at this is this thing called electronegativity difference. Okay, so electronegativity difference is just that. We look at the electronegativity values for the two things that make the bond. And if the difference is really large, we say it's an ionic bond. Careful, there are always exceptions to that, and I'll show you some. But I'm just going to pull up here. Oh, come on, where are you? Maybe I have to click out of what I'm filming, and I shouldn't have to. Yeah, I'm going to have to, because it's just being a pain in the butt key. Here. Nope. There. Sorry. So here's my image. We're going to have two full screen snips going here, guys. Let's get some, really cool stuff. Now I have to remember how to switch back and forth between the two of them. Okay, so that wasn't what I wanted to do. There we go. Here's a table of electronegativity. You've got one in your book, right? You can look up one. You can Google one. If you feel like you really want to have one that you want to print out, you can do that too. You don't need to. You can just look them up. But if you notice, we said fluorine's the highest at 4, set at 4. We said down in this end, these are the lowest down here. We've got francium, cesium. We don't really talk about that, though. If I take the difference and I say calcium fluoride, I'm going to have calcium bind with fluorine, right? Of course, if we're going to write that formula, we'll practice that. 2 plus minus. So then I'll have CaF2. The two atoms that bond are calcium and fluorine. So I have an electronegativity of 4 and an electronegativity of 1.0. If I take this difference, it's 3.0. It's much greater than 1.7. So that is definitely what we call high ionic character. What that means is that there's such a difference in electronegativity, you definitely will have that electron moving over to the fluorine. You will have a positive and negative charge, right? A cation and an anion. And that will make a crystal, because ionic makes a crystal. You can have different amounts of differences that come closer to 1.7. So on that scale, if you were to take two things and take the electronegativity difference, anything that is greater than 1.7 is considered ionic. Okay. The greater the difference, so the larger that value, we say the more ionic in character it is. Now this is relative, because you can have something that is not ionic, and they'll still ask you which one has the greater ionic character. So you have to kind of equate that when they ask you about ionic character, so when the question is about ionic character, you have to think in your brain, oh, I got to look at electronegativity difference. Now, I'm going to abbreviate this in the future because I'm a chemist and I hate writing English. Right? When we talk about electronegativity difference, I use En for electronegativity. And difference is a delta, right? If you think back, the Greek letter delta, which is like a triangle, means difference in math. You take the difference, take the delta. So I will use delta En, difference in electronegativity value. We can look at other elements around here. We can pick other ones, but as long as you have a metal with a nonmetal, you will have ionic. right? So I'll take, why does oxygen look like a D on this? I just noticed that. It didn't print very well on this particular one. This should be oxygen over here. Rib big O for oxygen. and, so if I even do something like magnesium oxide, right? Magnesium oxide, well, MgO, I have 1.2, I have 3.5. If I take the difference, I'm going to be what, 2.3? Right? The difference between this is 2.3. So that's still greater than 1.7. I can even do something, and if you look, guys, this is metal with non-metal. That's really the big thing to be able to tell. If you have a metal with a non-metal, that is going to be ionic by definition. You look at the electronegativity difference, that tells you just how ionic it will be. I can take something like, molybdenum oxide, right? Molybdenum, and we're going to use molybdenum 2 oxide, right? So that's molybdenum 2, because it's going to be a plus 2. Just for ease of writing the formula, I have 1.8 and 3.5. Okay, now this difference is going to be a little bit smaller and right on the cusp, really. This difference is going to be 1.7, but it is a metal with a non-metal, so we say that is ionic. Now, when you get to things like here, where you have metals and you have oxygen, that difference is going to get smaller and smaller. Still going to be considered ionic, but it'll have very little ionic character compared to like MgO. It's a relative comparison. So just remember that electronegativity scale is a comparison scale. Okay. Hold on a second. Let's go back to that. Am I in that? No, what did I just do? Oh, I know what I just did. Hold on. Go back to my full screen snap. And that's what I thought happened. I want to do this. It did close my other one out. Shouldn't have, but it did. Alright, so we were talking about the fact that ionic is a transfer of electrons. When you do this, you have certain characteristics to the material. Things you have to memorize for the characteristics. So these characteristics that are listed here, and I know you might have to squeeze them in, but you can also put them off to the side if you want. It goes by this thing called being crystalline. It makes a crystal. This is a representation of a crystal over here. Opposite charges next to each other. They make a very rigid structure. The electrons are fixed as a solid when you have that structure. When you dissolve them in water, though, the electrons can start to move through the water, and then you get conduction of electricity. I have to try to remember to show you these tomorrow about the traits and show you the difference between pure water's electronic conduction versus adding salt water to it and having conduction. And I gotta be honest with you, my deionizer isn't working that great, so we may still have conduction, because if there's any sodium in the water, it'll conduct. So ionic things have crystalline nature, very high melting point, will not conduct as a solid but will as a liquid, or AQ, either one. So liquid allows the electrons to be able to pass along the electricity. They're free to move and bump into each other, where when you're rigid in a crystal, you're not. And ionics will definitely dissolve in water. So that's another trait you look for when you're given an unknown, which you will do next week. So that's ionic. That is one type of bond. Then we're going to move on to the next type of bond called covalent. I don't know if I can really get this on a whole screen, so let's see if I can. I'm going to stick that down. I don't know. We'll try. A lot of times when I do screen snip, it shrinks what you can see, and it's hard to get it all. Here, okay, let's. All right. Ooh, my power just came on. Yay! So, the covalent means to share electrons. The electrons do not go from one thing to another, and you do not have strong Coulomb forces then. In fact, we don't talk so much about the force between these being Coulombic. In ionic material, we look at Coulomb's law, we modify it, we call it lattice energy. In something that's covalent, we don't talk about lattice energy. We talk about the attractive forces depending on how well the electrons are shared. So, big for you to know is covalent is electrons are shared. Okay, a huge thing to know. Excuse me. Now, you can have sharing that is equal. Okay, so equally shared is called nonpolar. There is no shift in the electronic nature of the atoms. There's no movement to one side or the other of a bond of the electrons. They buzz back and forth equally. When you make a bond and electrons are shared, you can have two atoms of the exact same identity. The electronegativity will be exactly the same because they're the same identity. So the little electrons in the electron cloud that are buzzing don't know whether they should spend the time here or buzz around here. So they buzz back and forth. And when they buzz back and forth, when you look at the mathematical models, they are spending equal time around this guy versus this guy. And your cloud, the electron cloud, does not shift. That's called equal sharing. And I don't know why in AP they set the measure of the cutoff for whether they're shared equally or not to be 0.4. The problem is that even if you have a very, very tiny electronegativity difference, one of the atoms is going to get those electrons just a little bit more than the other one. So it truly isn't completely shared equally, but in chemistry we call it a dipole moment when the electrons move to one side of the molecule or another. Okay, so a dipole moment, and I'm going to get into this even more later, is when the electrons move from one side to the other. And that's, I'm simplifying, it's a little more mathematically complex than that. But you need to know that word so you no longer have even distribution of the electrons. So this is so small a difference. Your dipole moment is very tiny. So a lot of times on higher level college texts, a college text versus a high school text, they'll say, oh, there's this range where you really say it's not polar. It's nonpolar. Okay, what I'm going to tell you is, if they're the exact same nonmetals, that is definitively a nonpolar covalent bond. Okay? That's the one to really go by. That's the biggest thing to think of. It is truly a nonpolar covalent bond. Now, if you have two nonmetals that are different and have a large enough electronegativity difference, then you have what's called a polar bond. Polar bond. Okay, so polar, if you think about a magnet, you have poles, right? You have a positive and a negative pole on a magnet. You bring the two like ends together, they repel each other. You flip a magnet around, now you have to bring opposite charged ends together, they attract each other. Okay, polar covalent is kind of like that. Your atom has partially charged ends. I stress that. Partially charged ends. we represent that with, and I'm going to have to find, there's a great AP video that I'll assign to you probably over the weekend. It's a 5-minute video, so it's not a really long video. And they talk about these dipole moments. Okay, now, these partial charges are represented by this wonderful little letter there called lowercase delta. Okay, because big delta, right, capital delta, like a triangle, and I'm writing it this way. Here's my bottom of the page because I'm at a slant. So that delta, this is capital delta, and I'm going to change my size of my tip. I had changed it because, oh, I must be in my highlighter. I'm so silly, that's my highlighter, but it'll still work. Okay, this is delta. That's capital delta. This is lowercase delta. It looks like a D with a little handle on it. So you can almost write it that way. I mean, it's got that little swoopy thing. It almost looks like a weird musical note. This means partial. This delta means big difference, right? There's an actual difference. This means partial difference, just a little bit of a difference. So, semantical, I guess, I don't know. We say that we're going to have a slightly negative end and a slightly positive end, which is very different than ionic because you have a real positive and negative. All right? When you have to label them, the one that has the lower electronegativity value will be the slightly positive end. The one that has the higher electronegativity value will be the negative end. Here's hydrochloric again. When we look at that molecule and we look at the electronegativity values, chlorine has a higher one, so the electrons are said to flow towards chlorine. This little arrow means electron flow, and the arrowhead will be the one where the area is negative, and to indicate the positive side, they put this little thing on the end of the arrow, and that means that's the positive side. So you say, oh, in my molecule hydrochloric acid, the electrons think chlorine's really cool because he's got a higher viewer rating of 3.2. So we're going to hang out with this dude because he's got a higher viewer rating, higher electronegativity value, right? Poor little hydrogen's like, nobody comes and sees my website. And every once in a while, one of these will buzz around here, and then they go back. And then every once in a while, they buzz, and they go back. And you get this weird distribution of electron cloud that looks like this. Like you got a little bit of electrons there and a lot over here when they plot it over time. Okay, it's kind of weird looking, but that's what it looks like. Okay, polar covalent, again, is this unequal, like a tug of war. One of them wins, one of them gets the electrons. This is water over here. Oxygen's the more electronegative, so the electrons flow towards oxygen in each one of these bonds. So that's why you have the minus and positives, and that technically this is partial minus and this is partial positive. Okay? Now, characteristics of covalent. Got to know these, just like you have to know the characteristics of the ionics. Covalent is not a nice crystal. You sometimes can have some of them, like sugar can be. But most of the time they're not crystals. They're very brittle. They break apart. They can be crushed into a powder really easily, like between your fingers. They will not conduct electricity. They don't conduct heat. They're insulators. Could you guys know that term? I hope you know that term. An insulator, to insulate, is to prevent conduction. And I'm a horrible speller, and that does not look right. Insulate. I'll have to look it up. Okay, so that's a big thing. If something does not conduct electricity or heat, you start to think covalent, 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 and it could be either polar or nonpolar. It just depends on another thing. Nonpolar will not dissolve in water, but polar will. And the reason is water is polar, and like dissolves like. So we use this very generically. It's a general type of description, but the reason is similar bonds interact with each other. A polar will surround another polar and pull it in, so the water will pull it into solution. But a nonpolar can't do that, so it won't dissolve a polar, and vice versa. Okay? And the other thing is really low melting points. Really low. And you'll see that when we do a lab, and you've got to figure out, do I have a polar bond or a nonpolar bond? Okay, so the big difference between polar and nonpolar, big difference between the two. See if I can get a really good color here. Really isn't a great one. We'll go with a little hot purple or pinky. The difference between these two has to do with dissolving in water. Okay, that's a big difference. And this word is dissolve. It got cut off and got scanned in. Okay? Now, this next one, coordinate covalent bond. Basically, the only thing you need to know about a coordinate covalent bond is that it exists in polyatomic atoms. That's the big thing. That if you have a polyatomic ion, inside the ion, it is covalently bound. The ion to something else is an ionic bond. So, coordinate covalent leads to a compound that contains both ionic and covalent bonds. Okay, so that's the big thing that's written right here. That's the takeaway moment. Takeaway moment contains both ionic and covalent bonds. A coordinate covalent bond itself, by definition, is a bond where one of the atoms contributes completely to the bond in terms of electrons. So here's little hydrogen, who's an ion that's positively charged, has no electrons. Kind of boo-hoo, electron poor, kind of out in the outs, a little down on its luck, doesn't have any electrons. And then you have ammonia, which is what we call electron rich. There's a free pair of electrons not involved in a bond sitting on the top of the nitrogen. And a little hydrogen goes, hey, what you doing? And all of a sudden it's like, I'm going to come over here and I'm going to attach myself and find my little sugar daddy of electrons. I'll bring nothing to the bond, nothing to my relationship, and I will just mooch off of the one with all the electrons. So that's why I call it the moocher bond, because this little hydrogen is just sucking the electrons away, in a sense, from the nitrogen. And when that happens, you get ammonium. So that makes the polyatomic ion. All right. I'm going to move this up because the next thing we're going to talk about is metals. All right. So the last type of bond that we have to talk about is metallic bonding. And a metallic bond comes from a metal. And it is described, and these are the keywords, guys. Look for these keywords. I can't stress enough, these ones right here. If you ever see anything talk about a mobile electron, a sea of mobile electrons flowing between two positive atoms in a sheet, it's mobile, the electrons get to move. That is a metallic bond. Because these electrons can move freely and they're not fixed in a position, they can essentially bump into each other and carry along electricity. They can carry along heat because they can move. So metals have these great points over here that you have to be able to read and say, oh, that's a metal, bright and shiny, because the electrons can move. Not only can they move, a little photon can eject one for the photoelectron effect. That cannot happen very easily in a solid ionic substance. Very rarely do you see that happen. It'll be shiny, it'll conduct. We make pans out of metal because they conduct the heat to cook. Copper, Revere pans. Revere pans were coated with bottom on the copper because copper's a great conductor. Copper's kind of a soft metal, so it's not very resilient. So you make the rest of the pan out of something else, and then you coat the bottom with copper so it evenly distributes the heat. Okay, so copper is a very popular way to get heat to distribute nicely on a pan. You can pound them into shape that's malleable. Wow, that's great for making a pan because you can pound it into the shape of whatever container you want to cook with. You want a wok, you pound it into a wok. You want a baking tray, you pound it into the baking tray. It can be drawn into a wire. Most of your electrical wiring is copper wiring in your house. Until recently, phone was copper wiring. It carried the sound because it's a conductor. We're getting away from that. We're now into what's called fiber optics and other types of cables that can carry the sound, carry your voice, digitize it, redigitize it on the other end. So it's a little different now, but it was all copper wiring before. And they do react with acid. This is a big thing. They react with acid. Okay, now there's another type of material called a network solid. A network solid is made of covalent bonds, but the way the solid is made, it actually forms a crystal, and it doesn't behave like a covalently bond material. And that's called a network solid. And I don't have that in here. We'll talk about that more later when we do our lab, and that's going to be tough because when you go to do the lab, you're asked to identify things, and I will always say to you, if something doesn't fit in, if it's not seeming to be correct, think network solid. Okay, let's get to what holds the crystal together for an ionic substance. What holds it together, and with this transfer of electrons, because remember we said the electrons go from one thing to another, okay, they transfer, right? Metal to the non-metal. Metal loses, non-metal gains. Metal becomes, non-metal. Metal becomes positive ion. Non-metal becomes negative ion because it gained the electrons. What holds it together? This baby. Lattice energy. Because, I should have done that because I got red writing. LE for short. So I'll go over that with a black pen so you can see it. Right? Lattice energy. This is modified Coulomb's equation. It is a force of attraction. Then what's the modification? This thing. It's not R squared, it's R. Could you use Coulomb's force to describe how much attraction exists in a lattice? Yes, you can. Okay, so you're like, I don't want to know lattice energy versus Coulomb. You can still talk about Coulomb's attraction in a lattice. It'll still work. They prefer, when you're talking about a crystal, to use lattice energy, but I think you would get the points if you use Coulomb. So, what is lattice energy? Well, it's the charge of your first ion times the charge of your second ion. And this is more than a particle. It's your ion here, okay? So these are talking about the ions on the top because we're talking about lattice energy. And the distance between them. Again, like our distance before, except it's not squared. So if you read about the lattice energy in your textbook, you will see it's not squared. I'm going to move this up a little. Trending. All right. Prediction what happens. Wow, this is acting really weird today. And it just has to be the day. Okay. So prediction of what happens. Think about the setup. If I change the value of the charge, I change my numerator. So if I go to larger charged values, my numerator will go up. So the lattice energy will go up. If I go to a larger diameter ion, then, and that happens with larger charge. Well, I shouldn't say it happens with larger charge. Depends on what we mean by larger charge. For instance, this comes to with your periodic table, and I closed it out. We have a little periodic table. and we have these two rows over here, columns over here. If I pick something down here, its R is going to be bigger than up here. It'll have the same value here, but my R will be bigger. So my charge, even though this will stay the same, this will get bigger, and my value will go down. But if, let's go to a different way, let's compare this and this to something over here. Okay, this could be our negative. We're saying the Q, this stays the same. So this would change, and our R would change a little bit too, because this R will actually get smaller going this way, but your Q value will go up. So this is going down and this is going up. So our lattice energy will end time going up as well. Okay, so again, this is manipulating it, thinking this through mathematically. I change this number, I make it bigger, what happens? Oh, I take that number and make it smaller, what happens? And that's really what this is about. The bottom table can really be an example of that. And often, guys, AP will ask you, this is not a Regents issue, this is AP. AP will ask you, why is the lattice energy different? Why does one have a bigger energy? Why does one have a smaller energy? So it has to do with what is changing when you compare the two. So if I compare these two, right, they're both attached to chlorine. One's lithium, one's sodium. Lithium is a smaller ion. It's further up on the table. It's got lower energy value, lower energy levels, right? So lithium is smaller. This guy is smaller, right, than this guy. So if that's the case, that Q1, Q2 over R, that's smaller. If that's smaller, this number becomes bigger. Right? I'm dividing by less of a number. So if they say why there's a difference between these two, you look at positioning and go, oh, what's changed? These are both +1 and +1. And you have to say that too. You have to say, oh, this is +1 and +1. So you have +1, +1. I got +1, +1. They stay the same. But my R changes, so that is the biggest thing contributing to the difference. You can do it across the table too. Like I chose this one and said, look at the difference between these. They're both chlorine, again, but one is sodium and one is magnesium. Now the charge changed. Okay, so the charge changes, and actually your R will get a little bit smaller too, because the Mg2 plus is smaller than an Na plus. So that goes up. And if you notice, this is 2, and this is more than 2. It would have been 1400 if it was just twice the difference. But that other addition has to do with the R change. If we look at these two, right, magnesium smaller than calcium, so the value is going to be bigger. It's not that much smaller, and the charge hasn't changed that much. So it's just the radius that contributes there. Okay, so that, and guys, you have to know this. You have to be able to explain. That is a key. So think it out. Think it out. Okay, I know I'm getting kind of long-winded here, but let's see something. Oops, wrong one. Sorry, guys, I'm still having issues with my computer, and I know it's operator error right now. I know I'm just having one of those days. We're going to stop there. That's enough for tonight. We'll go on later.